If you see that there can be two kinds of reactions, right? So we are
Yeah.
doing the equilibrium portion with the Q and the Kc. If you see the reactions, any reactions can be of two types, right? They can be irreversible reaction, right? There can be reversible reaction, right? There can be two kinds of reaction: irreversible reaction and reversible reaction. Understood, right? Now here it's a very important thing we have to notice, right? That if you see that the irreversible reactions are those maximum reactions which happening around us is irreversible reaction, right? And so if
Yeah.
you see that when we talk about irreversible reactions are those reactions which goes to completion, right? We denote via singular arrow, right? A goes to B, right? There's another
Yeah.
reaction which happens, right? Reversible reaction, right? What's a reversible reaction? A reversible reaction is a reaction which has got both forward and backward direction, right? Number one, right? This is very crucial, right? Which is good for both forward and backward direction. Now, if we put a reversible reaction in a closed system, right? That's very important. Now going to this thing, so we know that reversible reaction features are what? That they have got both forward and backward direction, right? Hmm? Right. This is clear. Now, second, now if the forward direction is endo, the backward direction will be exo. This thing you have to learn, right? If the
Yeah.
forward direction is exo, the backward direction will be endo, right? Isn't it? And the same amount of energy will be transferred both the sides, right? Is it clear? And the same amount of energy will be transferred both the sides, right? Means if it is endothermic by plus 122, it will be exothermic by minus 122 in the backward direction, right? Understood this part, right? Now going to this part. Now next is that if we keep a reversible reaction in a closed system, right? We're keeping a reversible reaction. We're taking a reversible reaction and putting in a closed system, right? Closed system. A closed system is what? A closed system is a system where heat can go out, mass cannot. Okay, so that's a
Yeah.
reverse. That's a closed system, right? You need a closed system also for the reversible reaction to attain equilibrium. If we keep a reversible reaction in a closed system, it can attain equilibrium. We tell, right? It can attain equilibrium, right? Did you get my point, right? We talk like this, right? If we keep a reversible reaction in a closed system, it can attain equilibrium. Hmm. Now, what is the equilibrium, right? Now, suppose you're putting A and B, right? We're putting A and B, right, in a closed system. Suppose we started with 100, right? Is it clear to you? Now we have to
Yeah.
know this important discussion. Then what? If you speak about rate, right? Rate tells you that how fast a reaction is, right? How fast a reaction is, right? Clear? Understood? If you see that when we talk about rate tells us how fast a reaction is, right? How fast or slow, right? If you call about equilibrium, right? Equilibrium tells you that how far the reaction has reached. Please note down this, right? How far the reaction has reached, right? Has gone. Reaction has gone, right? Clear? This is clear to you, right? This is clear to you.
Yes.
So if you see that, what does the rate tells you? Rate tells you how fast a reaction is, right? And what does the
Yeah.
equilibrium tells you? How far a reaction has gone, right? To completion. Understood this part? Clear? And if we
Yeah.
if we if we if we talk about enthalpy, right? Now, enthalpy is what? Enthalpy is that how how much heat content it has, right? That's it. So can you understand the difference? Rate as an equilibrium has got no relation. This remember this thing part, right? No relation. Rate is how fast a reaction is, and equilibrium is how far the reaction has completed. This is clear.
Yeah.
Understood? This difference
Yeah.
should be absolutely clear, right? They've got no relationship. They've got no relationship. That if the rate is faster, the equilibrium will be reached more. No, not really, right? Isn't it clear? Nothing.
Yeah.
And having said this, suppose you have taken 100A. Suppose you have gone to the lab at around 8 a.m. and added 100A to the to a beaker, right? Closed system, right?
Yeah.
Now the rate of the forward direction will be very high, right, at the time, because we have to know these content, that concentration will be directly proportional to the rate, right? Isn't it?
Yeah.
The if you increase the concentration, right? If you increase the concentration, the rate increases. Clear? Now,
Yeah.
pressure. If you increase the pressure, the rate increases. We learned this, right? If we increase the surface area, the rate increases, right? Fine. If you increase the temperature, the rate increases, right? Understood? We know this. So we
Yeah.
have to plug in this concept now over here. If the concentration increases, the rate increases. So if the concentration decreases, the rate, tell me, decreases. Understood? Clear? Decreases. So this is a concept we have to master, right? Now going to the next part, right? If you see when we talk about the when you talk about the concentration, right? So concentration, if it is more, the rate will be more. Concentration decreases, the rate will be less, right? Now, suppose you have gone to the lab around 8 a.m., right? And you have started with 100 a. So at the start, this is rate I'm drawing, right? This is rate I'm drawing. This is the time, right? Understood? This time.
Yeah.
Now, suppose you have gone to the lab at around 10 a.m. and you have added 100 a, right? You have added 100 a. So what happens? That at the forward reaction will be very fast. The backward reaction is zero, right? See, understood? Understood. This clear. This is the forward reaction. It's very high. The backward reaction will be zero because we have not taken any B, right? B is zero. Got it? Did you get my
Yeah.
point, right? The B is zero, right? Isn't it? So the backward reaction rate will be what? This will be zero. Understood, mine? This will be rate of the backward reaction will be actually zero, right?
Yeah.
Now at around 9 a.m. you have gone to the lab. Suppose 20, 10 got transferred, right? 90, 10, right? So the rate of the forward reaction will decrease or increase? Please tell me.
It will
109. It will decrease, right? It will decrease, right? Now, the rate of the backward reaction will be increasing or decreasing? Tell me. It was
decrease.
0, it was 10. So it will increase or
In,
decrease? Increase, isn't it clear? Now,
yeah.
again, you have gone to the lab at around 10 a.m., right? Hmm. And suppose 10 got transferred, right? 80, 20, right? Understood. Fine. Now, what happens? Tell me. The rate of the forward reaction will decrease or increase? Tell me.
Decrease.
Decrease. And rate of the backward reaction will decrease or increase? Tell me.
Increase.
Increase, right? Clear? Fine. Now, again, you have gone to lab around 11 a.m. Now it is 70, 30, right? So the forward reaction will decrease again,
Yeah.
and the backward reaction will increase, right? Understood.
Yeah.
Now at this point of the time, we see very, very unusual circumstances. At this point of the time, at around 11 a.m., the rate of the forward reaction becomes equal to rate of the backward reaction, right? Equal to. Now, again, we are going to the lab around 12 a.m. Suppose the forward reaction is suppose 80. This is suppose, sorry, we measure 70, 30, right? So here we are seeing an unusual thing that when the rate of the forward reactions became equal to rate of the backward reaction, right? The concentration did not change. Can you see this? Now concentration is not changing. Again, we do our trial at around 1 p.m. 70, 30, right? Got it? The concentration is not changing, right? So we can tell what? That the reaction has achieved equilibrium, right? So at
Yeah.
equilibrium, what are the salient features you have? At equilibrium, we have got the rate of the forward reactions becomes equal to rate of the backward reaction, number one. At
Yeah.
equilibrium, what do you find? The concentration of the reactant and concentration of the product, right? Right? Remains constant, right? Fine. Is it clear? Do you get my
Yeah.
point? Do you get my point? So this is a very important portion we have to learn, right? That what are the salient features of the equilibrium then? At equilibrium, we know that it has to be a reversible reaction, right? First, the
Yeah.
reversible reaction has to be put in a closed system. Agreed? Finally, when you give sufficient time, it can attain equilibrium. At equilibrium, what do we find? We find that the rate of the forward reaction, right, becomes equal to rate of the backward reaction. Fourth, at equilibrium, the concentration of the reactant, right, concentration of the reactant and concentration of the product will remain constant. Is it clear? Remain constant, not equal, right? Constant. Is it clear to you? Now, if we see any reaction, reversible reaction, it can attain equilibrium, right? Isn't it? So the salient features are what? Salient features are these which I've discussed, right? And we have to know that equilibrium is dynamic in nature, right? Although the concentration of the reactant and concentration of the product is not changing, right? Understood?
Yeah.
But still the reaction has not stopped. The reaction is still going on. Since rate of the forward reaction is equal to rate of the backward reaction, the rate at which the A is getting disintegrated to form B, at the same rate B is getting disintegrated to form A, right? Is it clear? So the same amount of the reactant and product concentration will be observed, right? Fine. Now we have to know a definition called as equilibrium position, right? Position. So you know that what is equilibrium position? Equilibrium position is a proportion, is a what is going to equilibrium position is the proportion, right? Proportion of reactant concentration and product concentration at equilibrium, right? Clear? You get my point? Understood this part? What is equilibrium position? Equilibrium position is the proportion of the reactant concentration and product concentration at equilibrium. Clear? Now,
Yeah.
in that earlier example, what was the equilibrium concentration of A? I took the example 70. Concentration of
7.
B is 30, right?
Yeah.
So equilibrium position of what? It's the proportion of the reactant concentration of the product and reactant at equilibrium, right? The equilibrium position will be also tell you that where has the equilibrium been reached, right? Clear?
Yeah.
Suppose you're having A goes to B, right? A goes to B, right? A goes to B. Understood? Understood. A goes to B
Yeah.
and B goes to A. Now you have to understand that if the reactant concentration is more over here, see, the equilibrium position will be lying towards the, tell me, reactant, right? Clear?
Reactant. Yeah.
If the product is greater than the A, right, of the reactant, right, the equilibrium position will be towards the product, right? And product
Yeah.
will be more in the reaction mixture, equilibrium mixture, right? Is it clear? What is the
Yeah.
equilibrium position? It's the proportion of the reactant and product concentration in the equilibrium mixture at equilibrium. Fine.
Yeah.
Understood. It can be anywhere. Equilibrium can be reached towards a reactant, can be reached towards a product, anywhere it can reach, right? Clear? To get my point, right? And always remember that whenever whenever we are finding out the equilibrium, that where is the equilibrium lying, the mixture will be telling you, right? Is it clear? You get my
Yeah.
point? So these are the salient features which are there, and this is very important. The concentration of the reactant and product remains constant, right? Hmm.
Yeah.
Right. Now we're going to the next part. If you see, when we talk about when we talk about the when we talk about the equilibrium constant, this is very crucial, right? That if a reaction we are taking AA plus BB gives you CC plus DD, right? We're getting this reaction, right? Fine.
Yeah.
Clear to you? Now in this reaction we are seeing what? In this reaction we are seeing that the equilibrium constant will be equal to what? The equilibrium constant will be equal to product to the power of stoichiometry. Understood? Clear? Understood?
Yeah.
By reactant to the power of stoichiometry. Is it clear? Understood this part? Got it? The equilibrium constant will be what? Now,
Product of
product to the
24.
power of stoichiometry by reactant to the power of stoichiometry.
Yeah.
And over here, what we have to do? We have to replace the concentration, right? We have to replace the concentration. Sorry, we have to put the concentration when it reaches equilibrium, right? Fine. Is it clear? Not any other concentration values we have to put over here. Is it clear? This important part, this important bit is clear, that we have to only put the concentration of the reactant and product when it reaches equilibrium, right? Clear? Not any other. See, we did now 100, 10, 100, 0, 90, 10. It was fluctuating. See, 80, 20, 70, 30, 70, 30, right? 70, 30, right?
Yeah.
70, 30. Is it clear? So we have to
Yeah.
note down this, that this is the equilibrium concentration, right? Do you get my point? Do you got my point? We have to replace concentration. What concentration? Equilibrium concentrations we have to replace. Fine. Is it clear
Yeah.
to you over here? Now going to this thing, now you have to see that your pen is connected, right?
No, so wait, let me do.
Please, thank you so much. You connect.
F.
So we solve this like this, right? Very good done, right? Well done, right? Yeah, again you're doing a mistake. See,
Yeah.
equilibrium sign, it's the equilibrium reaction, right? Equilibrium constant, right? Write down the equilibrium constant for the following expressions. So following gas combine
Yeah.
to form, say, now to balance it, you balance it. To balance it, put 2 in front of it, right? 2 in front of it, and after that, yeah. After that, balance fluorine. Yeah, that's all, right? Fine. So this is the thing we learned, right? Isn't it? Now, if you see then after that you can do, right? KC you can do, right? Always write down this is equilibrium concentration. EQM, right? Fine. This is the thing you have to learn, right? EQM, right? Fine. You get my point, right? We
Yes.
said EQM over here, right? Fine. Now over here, see, we have to understand that you know what, that equilibrium can take seconds to reach, right? Isn't it? We have to know this important fundamental, that if we see that this is the way we do it, right? Painful way, that we have to measure the concentration constantly, right? Isn't it? To measure the concentration constantly, we have to measure the concentration, right? Fine. Constantly we have to measure the concentration, 70, 30, 70, 30, right? Till the time, see, till the time the concentration becomes constant, right? Is it clear? We have to constantly measure till the concentration becomes what? Constant, right? Not equal, right? Constant. So the equilibrium can take minutes to reach, seconds to reach, can take hours to reach, can take days, can take months, can take years also to reach, right? Isn't it? See,
Yeah.
see this reaction. This is rusting of iron is also equilibrium reaction, right? Isn't it? It's an equilibrium reaction. It take years to reach, right? Isn't it? So how
Yeah.
long shall we? How long can we? Shall we measure the concentration, right? How long can we measure the concentration, right? Is it clear? So
Yeah.
so this is a very important fundamental you have to understand that how long can we measure the concentration? This is thing. Can we have any other parameter where we can know that how far is the equilibrium to be attained? How far is the reaction to attain equilibrium? Do you get my point, right? Do we can we have something to measure that, okay, that how far is the reversal reaction to achieve equilibrium, right? Yes, we
Yeah.
can, right? What we do? We measure what? We measure Q, right? Isn't it? We measure the Q, right? Now note down a very important thing that equilibrium constant, right? Equilibrium constant does not depend upon concentration change, does not change with pressure change, does not change with does not change with the surface area. Doesn't change with catalyst. It only changes with temperature, right? Fine. Note down this, right? So equilibrium constant only changes with temperature. Now going to this thing, now we have to see that when we are seeing this, right? We have to also understand how to measure the Q, right? What is
Yeah.
Q? You have to understand this part that if you see that when we talk about the Q, right? We talk about the Q. Suppose we are seeing that we are trying to analyze a reaction, right? Suppose this reaction, right? Okay, if we try to analyze this reaction, that okay, that we are trying to do an experiment with it, right? So we will be having a designated Kc value at a particular temperature. Got it? We will be having a designated Kc value at a particular temperature. We will have, right? Isn't it?
Yeah.
Now we do the same reaction in our lab at this temperature. Hmm. We have got the literature value of the Kc, right? Now, at around 7 a.m., we have gone to the lab, right? At around 7 a.m., we've got to go on to the lab and taken the concentration reading, right? Hmm.
Yeah.
Suppose we have gone to the lab, suppose at around 4 p.m., and again taken the concentration, right? Hmm. Right? Is it clear?
Yeah.
You get my point? We are again taking the concentration, right? Now, here it's a very important part you have to master, right? That we now are putting these values into a new expression. It's similar to the equilibrium constant, exactly same. But in the equilibrium constant, this is very important. You must have to put equilibrium concentration, right? You cannot
Yeah.
put any other concentration. You have to put the equilibrium concentration, right? Clear?
Yeah.
This is clear to you? You have to put the equilibrium constant, right? Concentration, right? Clear this is? Is it
Yeah.
clear? We have to put. Now this is very important that actually whenever we are seeing that the values we are taking, right? We don't have to put the equilibrium concentrations over here, right? Understood? Clear? This is
Yeah.
clear to you? That's
Yeah.
Q, right? Q is the reaction quotient. Reaction quotient, we put the concentrations as it is, right? What we're getting, right? See this, right? Did you understand this part, right? This
Yeah.
understand this bit. So we are getting this, right? Now again, I'm going Q. I'm putting the concentration, right? Isn't it? So this this, right? I'm putting it, right? We're getting this value, right? Clear?
Yeah.
Fine. Now going to this thing, if you see that when we talk about when we talk about this Q value, we know the Kc, right? Now you have to do this trick. Now suppose Kc is how much? 49.5, right? Kc is 49.5, right? Now
Yeah.
how much is the Q you are getting around 7 a.m.? 4, right? Always draw this line, right? 4. How much you are getting the Q at around 4 p.m.? 103, right? So we can tell that at 7 a.m. the reversible reaction is not at equilibrium. It is moving to which direction? Forward direction to achieve the
Oh.
equilibrium. Understood? Clear? It's not at equilibrium. Always draw this line. It will be very much easier. Now at around 4 p.m. we're getting 103. We tell that the reversible reaction is not at equilibrium. It is moving to the left or towards the reactant to achieve the equilibrium. Right? Do you get my
Yeah.
point? Do you get my point? So always try to know that if the reaction is moving to the forward direction, always write this. Q will be less than Kc, right? Is it clear? If the
Yeah.
reversible react, this thing you have clear because Le Chattel principle question will be seeing, right? You'll be seeing the Le Chattel principle question, right? That always remember that they'll be asking that we are changing the concentration, right? Isn't it? Suppose I'm taking that suppose I'm taking this reaction. H2 plus I2 gives you HI, right? They're saying that we are increasing the concentration of H2. So when you increase the concentration of H2, which direction it moves? Tell me. As per LCP,
Right.
moves to the forward direction. So they'll be asking that what will be the Q. So obviously, if a reaction is moving in this bit, you understand. If the reaction is moving the forward direction, what happens? Q will be less than Kc at that time. Understood? Clear? Do you
Yeah.
get my point? Now, if we change the HI and suppose increase it, so the reaction will be moving to the backward direction as per Leschet's principle. So what will it take? If the reaction is moved to the backward direction, what happens? Q will be greater than Kc. This bit you understand. This is a 7 marker question, right? 7 band question. Clear?
Yeah.
Is this concept clear? That
Yes.
Leschet's principle, you don't have to worry. If the reaction is moving the forward direction, so obviously Q will be less than Kc. This bit is very important, I'm telling you. Is it clear? Got it?
Yeah.
Did you answer this part, right? Thank you so much. See, now if we see that when we see any reaction, right? Isn't it? We can find out the Kc, right? Do one thing. Just do this bit.
No, you don't do it by
See,
checking it.
these are not the equilibrium constitution given, right? They are not, right? Is it clear? They're not the equilibrium constitution given. They're not, right? Hmm. You get my point? They're not the equilibrium constitution given, right? Isn't it?
Yeah.
Fine. Thank you. In this thing, we're getting what? In A, how much you're getting? How much you're getting this? Please guide me. Mine, can you hear me? Mine,
No,
can you hear me?
100.
Yeah, 100, right? So you have to, perfect, right? You have to wrote like this, right? Wonderfully done, right? This is the thing I'm trying to just follow this part, right? Wonderful, wonderful, right? Just remember that Le-Chattel principle, this concept, I'm again telling you that if the Le-Chattel principle you're applying and the reaction is moving to the forward direction, what happens? Q is less than Kc. This bit you have to understand. If your reaction is moving to the backward direction, Q is greater than Kc, right? Is it clear? Understood? Fine. So we are now if you see that whenever we are taking this bit is important, right? So if we have a reaction, right? If you have a reaction, right? AA plus BB is equal to CC plus DD, right? Isn't it? Now the equilibrium constant will be what? The equilibrium constant will be, please tell me. It will be C to the power C, D to the
Plus.
power D, right?
Yeah.
Divided by A to the power A and B to the power B, right? Isn't it? Fine.
Yeah.
Is it clear? Now, if you have got the same reaction, mind, if you got the same reaction, suppose the same reaction, but where the concentration is double, right? Isn't it? Concentration is double, right? Isn't it? Suppose you are, sorry, the reaction is inverse, my bad, right? Isn't it? If you're having the same reaction in this inverse form, same reaction in inverse form, other reaction, so you don't have to calculate the Kc of this reaction, right? Is it? The new Kc will be equal to what? Tell me. This new Kc will be equal to 1 by Kc, right? I
1
hope
by.
that you know this, right? Now,
Yeah.
if you have got the same reaction, but the another reaction you're seeing that the stoichiometry is actually double, right? Isn't it? Stoichiometry is doubled. You don't have to calculate the new Kc, right? Understood this part, right?
Yeah.
You get my point? It will be what? The
Yes,
Kc will
sir.
be equal to what? Kc will be squared, right? Isn't it? Right? Isn't it clear to you? Right? Now going to this thing, if you're having a reaction where the stoichiometry is half, this is very important. Halving the stoichiometry to square root the Kc, right? Clear?
Yeah.
Is it clear to you? Right? Did you get my point? Right? So what do you do? Wait. Over here. Just hold on. Just hold on. Did you get my point? This was a Q and the Kc part that will be clubbed with what? The Le-Chattel's principle, right? Take care of
Yeah.
that, right? Thank you.